Welcome back, class, to Fundamental Concepts in Chemical Engineering. Our first content lecture, beginning with our math and science review, which will be today on vector calculus. By the end of this video, you should be familiar with three-dimensional coordinate systems, the concepts of vectors in multiple dimensions, partial derivatives and gradients, multidimensional integrals, and the concept, though not the implementation, of line and surface integration. You are most familiar probably with two-dimensional Cartesian coordinate systems, where I have some plot where I have the origin, and I can move in the x and y direction, and I can write a function and determine a value as a function of say x to give y, or given a value at both x and y. We can also look at other coordinate systems, say a polar coordinate system, such as a circular or polar coordinate system shown here, that allows us to think about things in circles or on circles. Instead of having a value which is a function of x and y, we have a value which is a function of distance from the origin, r, and the angle from some sort of azimuth plane, referred to as theta. R, unlike Cartesian coordinates where x and y can be negative infinity to infinity, r can go from 0 to 2 pi, or higher orders of magnitude, but then you just end up going around in a circle. We can write similar concepts in 3 dimensions or higher dimensional space, and we can again think about things in Cartesian systems or polar systems. Starting with our Cartesian system, we can have a function that's derives from x, y, and z in that coordinate system. But when we move into our polar concepts, we have 2 major systems which are used. The first being a cylindrical system, which looks and assumes that a function has some sort of property that's well represented by a cylinder. In chemical engineering, this is most commonly, say, something like a pipe, where it's circular in one dimension, sort of linear in this other direction along the axis of the pipe. So here, we once again have around this circular part of the cylinder, the same polar system that we used in 2 dimensions, where we have r that goes from 0 to any desired value going outwards from the center of the cylinder, and then theta, which goes from 0 to 2 pi, which rotates around that cylinder. And then to tell you where you are along the axis of the cylinder, we have z. This can go from negative infinity to infinity. And we can say that the value of this function, the value in this coordinate system, is a function of r, theta, and z. Additionally, there's usefulness if we have something happening, say, in a spherical piece where we have something at an origin and something changes, or there's a function that deals with distance from that location. So think of this as maybe a Coulombic attraction, or a hydrogen atom, or any type of atoms where I have a nucleus sitting at this origin, and then I have some sort of spatial dimensions going out from that center. Right, so here I've drawn out a sphere. So here's in blue, we have the origin of the sphere, and we have our azimuth sort of a vector here. And so we again have r that points outwards from the origin of that center of the circle. We have this axial dimension that once again sweeps out the circle within the plane. So this is referred to now as phi, and it goes from 0 to 2 pi. And then to say where along this surface we are from sort of top to bottom, we now have theta. And in this case, it can only go from 0 to pi, because if I were to come around onto this side, that's just a rotation of around phi. So we say in spherical coordinates that the value of our function is a function of r, theta, and phi. So these coordinate systems are what we're going to use mostly in chemical engineering. In addition to saying that we have a value which is a function of x, y, and z, or r, phi, and theta, etc., we can also have what are called vectors. So vectors begin at the origin and then they point to some point in space. So here in Cartesian coordinates, I have this vector which starts at the origin and points to this dot, which is located at x equals 3 and y equals 2. So we say that that vector has directionality of this vector points at 3 comma 2. Vectors are going to have both a direction and a magnitude, right? So that this magnitude is how long this vector is, so how far it's pointing, and then the direction tells us where in space it points. I can draw this in polar coordinates as well, right? So in this case, this vector is pointing along r certain distance and at some angle around the circle. Within these, though, we can easily convert between our Cartesian and our polar coordinate systems by doing this recognition that any point in space, so or this vector has a x and y components. So if I'm in polar coordinates, or if I have information in Cartesian coordinates and I want to go to polar coordinates, I can use these functions that say theta is inverse tangent of y over x, and r is the square root of x squared plus y squared. And conversely, if I have the polar coordinates and I want to go to Cartesian coordinates, I can use the fact that x equals r. Just as I had in two-dimensional space, I can do this again in three-dimensional space. So here's a Cartesian three-dimensional vector starting at the origin and going to, in this case, 3 comma 3.5 comma 2. We can see that as I can take this vector, I can project the z component over here. I see that that aligns at z equals 2. I can project the down onto the xy plane, and I can see that x equals 3 and y equals 3.5. I can continue this concept looking at three-dimensional coordinates in say, cylindrical coordinates. So again, I have my vector pointing to this point in cylindrical space. I can find out its z position by projecting over onto the axis. I can find the r and the theta by projecting down onto z equals 0 and looking at what that r distance is and what the theta distance is. In this case, r is 0.5. Say theta is about 3 pi over 2 and z is 2. I can again convert between Cartesian and cylindrical coordinates, here shown as theta remains inverse tangent of y over x. R is again x squared plus y squared, and then you take the square root of that, and z just stays z. Lastly, of course, we have our spherical coordinate system. Again, we have our vector which points from the origin out to the point in space that we're interested in, and I can decompose that vector into r, theta, and phi components. Here we have our conversions, so theta remains the same, so y over x, and then take the inverse tangent of that. R now has both x, y, and z components, and phi is the cosine of z over r. Okay, so in addition to having just one vector in space, we can have what's called a vector field. So in this case, I have a series of vectors, say shown here, which are a function of x and y. So we can say that maybe at this point in space, so at -3, 1.5, there's a vector which points mostly in the x direction and none in the y. But at x equals, say, 2/3 and y equals 2/3, I have a vector which points both in x and y. Right? So we say our vector is a function of both x and y. And we see this a lot in things like fluid mechanics, where I have, say, a fluid element which is moving through space, and its velocity has, or sorry, its motion has both a magnitude and a direction, right? So sort of shown here, right? This I've got a magnitude and a direction, how fast I'm moving, and in what direction I'm moving, and that depends on my location in space. Okay, so now that we've gotten hopefully a review of three-dimensional coordinate systems and the concept of vectors under our belt, let's move on to thinking about derivatives and integrals. So applying these concepts of coordinate systems into calculus. All right, so as a brief review, hopefully this is very familiar, we can say that a derivative is a tangent line on a curve. So let's say I have this arbitrary curve, which is a function where we say y is a function of x. At any point along x, I can say, how does y change as x moves forward, right? As x increases, how does y change? In other words, what is the tangent of that curve right there? And we can formalize this to say that the derivative, so the change in y over x, sort of often abbreviated as y apostrophe, is formally the limit as the change in x goes to infinity, goes to 0. I'm sorry, that should be a 0 of y at x plus delta x minus x divided by the change in y. So as that distance shrinks to 0, how does y change? And from Calculus 1, you should be very familiar with how we can take various derivatives. So for any constant k, the derivative is 0. When I have a x raised to a certain power, I take that exponent, it moves in front, and then I subtract one off, right? So x squared goes to 2x, etc. Um, uh, the exponent e to the x returns e to the x. E to the kx returns via the chain rule, e to the kx times the derivative of what's happening up here. So the derivative of that would be k. So it's ke to the kx. The natural log of x is 1 over x. And then sine gives cosine, cosine gives negative sine. And then there's a whole bunch of other rules that hopefully you're familiar with. And you can, of course, look these up in derivative tables. So that my last comment, which is, again, hopefully just a reminder that our maximum and our maxima or minima occur where the derivative of dy dx, or d anything dx dt, etc., when that's equal to 0. Okay, so we can we've gone through and we've explained that the first derivative is our tangent to the curve, right? We can also take a derivative of the derivative. So this is our second derivative, abbreviated as, say, in this case, y, 2 tick marks equals d squared, right? Because I'm taking the derivative twice of y with respect to x. I can branch this out and say that I'm taking the derivative with respect to x of the derivative with respect to y, right? And so what the second derivative reveals is my curvature. So am I curving up or curving down? So if my second derivative is negative, then I'm curving down. If it's positive, then I'm curving up. And so you can determine um, if you have a maximum or minimum from your, when you're looking at your first derivative. So extrema, which have a positive second derivative, that's a minimum, right? Because I have to curve up from that point. And extrema with a negative second derivative will tell you that that's a maximum. Okay, and so of course we can take higher order derivatives, nth order derivatives. So y to the n is just continually taking derivatives of derivatives of derivatives. Okay, so we can do a similar concept in two dimensions. Let's say that I have a function where z is a function of x and y, right? So we can find out how z changes with x or y, right? So these are called partial derivatives. So because z is a function of both x and y, I'm only looking at how it changes in one of those dimensions. That's why it's a partial derivative. Okay, and so we instead of using a lowercase d to represent derivative, I use this sort of stylized lowercase d, which is going to represent that it's a partial derivative. So I can say what's the partial derivative of z with respect to x. So that's really I can plug this function in. So partial derivative with respect to x of f of x and y. I can also look at and see how does z change with y, right? So if I keep x constant, how is f of x, how is f of x and y, how is z going to change as a function of y? So partial z partial y is equal to the partial with respect to y of that function x and y. So this is only telling us how things move in a single direction. We also may want to know what is the direction and magnitude of the steepest ascent, right? So if I'm at this point, I want to know what direction and I'm moving uphill the most, and or sorry, what direction and how much I'm moving, right? So the magnitude of would be small over here and very steep or high over here. And so we call this the gradient. And so we represent this with this sort of upside down delta. So the gradient of z is equal to the partial derivative of our function with respect to x times x hat, x x vector, right? So that's saying this tells you what the direction is. This is in the x direction, plus the partial derivative with respect to y of our function in the y direction. Okay, let's go and look at how we can think about our partial derivatives. When I take my partial derivative of z with respect to x, I treat y as a constant. So for taking this derivative, y is in essence going to be the same as just a number, right? 5, except we're going to write it as y. Similarly, if I take my partial derivative of z with respect to y, x is treated as a constant. Okay, let's do an example. So we're going to assume that my function z is equal to x squared plus xy plus 2y plus 4. We're going to now look at each piece in this partial derivative, right? I'm going to take my function, I'm going to put it in here, and I'm going to look at each piece that's either added and subtracted and take the derivative, the partial derivative of that with respect to x. So let's look through these terms and see which ones are going to keep that, so that we're going to have to actually take the derivatives, and which ones are equal to 0. So if I look at this first piece, there's a term which includes x. It has to stay. I have my second piece, which is yx. It contains x. This is going to stay. Y is 0. Y is a constant. I then have plus 2y. this term does not contain an x. Therefore, the derivative is going to be 0. Similarly, if I have 4, that's a constant. It doesn't change with x. It's a 0. So if I go through here, now look at these remaining terms. If I take the derivative with respect to x, this should be 2x. If I take the derivative with respect to x here, it should be y. So my partial derivative of z with respect to x is 2x plus y. I can do the same thing in terms of taking the partial with respect to y of these terms. I can go through each one and determine whether y exists. So this first term, no y, it's going to be 0. This term contains a y, it must stay. We have to take the derivative. This term contains a y, it needs to stay. This term doesn't contain a y, it goes to 0. So when I take the derivative of these remaining two terms, right, the y goes away, I'm left with x, and the y goes away, I'm left with 2. So I end up with dz dy equals x plus 2. Okay, so just like in one-dimensional space, I can take multiple derivatives. So I could take a second derivative of my partial derivatives. So I could take the second derivative of z with respect to x. In other words, I'm taking the partial derivative with respect for partial z partial x. It's written over here. I can take this piece, substitute it in here, and then I'm left with the partial with respect to x of 2x plus y. Again, the y doesn't contain any x components, so it ends up being 2. This second partial derivative with respect to x ends up being 2. I can do a similar thing with taking the second partial derivative with respect to y. This time I take my partial z partial y, which we had over here as x plus 2. I substitute that into this piece. I then have partial with respect to y of x plus 2. There are no components that contain y. This second partial derivative is 0. However, these aren't the only two second partial derivatives that I can take. If you notice, this is only looking at x, and this is only looking in the y direction. We can, of course, look at how things change in the x and the y direction by looking at the partial with respect to z of both x and y. So we can break this down, right? So I'm going to take partial with respect to x of the partial z partial y. All I need to do again is take this term, substitute it in so that I'm left with partial with respect to x of x plus 2. 2 is a constant. The derivative of x with respect to x is 1. So my partial derivative of z with respect to y, then x, is 1. Okay, let's look and see what happens when I flip these around. Now I'm going to take the second partial derivative of z with respect to y and x. Again, I take the partial with respect to y of the partial of z with respect to x. I can go over here, substitute in my 2x plus y in here. I take my partial derivative. 2x doesn't contain y terms, that's 0, plus y. The partial derivative of y with respect to y is 1. So my partial second derivative of z with respect to y and x, x then y is 1. What you'll notice is that these are the same. And this is true of all partial derivatives. My order doesn't matter. If I take y then x, or x then y, I end up with the same answer. And this is true in higher dimensional space as well. We can extend these concepts to higher dimensional space. So let's say that our function isn't just dependent on x and y, but it's dependent on x, y, z, or x, y, z, q, or x, y, z, da, 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 all the way up to t, I can look at any partial derivative of that function um, with respect to any of its independent variables. Independent variable I'm interested in taking the partial derivative of. I treat all of the other independent variables as constants, and then I use one-dimensional differentiation rules like we showed much earlier. Okay, let's move on from partial derivatives and start thinking about gradients. Remember what I said before, that the gradient tells us the direction and magnitude of steepest ascent in a complex, in a multidimensional system. So if I have a function, say z, that's a function of x and y, if I'm at this point, I can say what is the direction of the steepest descent, so that I'm moving up towards this maxima. What is the direction of that, and how quickly am I moving up that plane? Okay, so let's go in and start seeing how we could calculate this. So let's assume that our function z is, again, x squared plus xy plus 2y plus 4. We can build the gradient from those partial derivatives that we calculated in the previous set of slides. So my gradient of z is, again, the partial with respect to x of my function in the x direction, plus the partial with respect to y of the function in the y direction. So luckily, we've already calculated what my partial z, partial x, partial z, partial y are in those previous slides, and I just need to plug them in. Remember, here's our upside down delta, which we'll call del. This represents the gradient. Okay, so I can take these terms. We already have those calculated out. I just plug them in. So del z, the gradient of z, is 2x plus y in the y direction, and x plus 2 in the y direction. Okay, so as we can see then, our gradients are vectors that are going to point and show us where we're going. Okay, I can do the same thing in higher dimensions, right? I could say take the gradient of a function, an arbitrary function w, which is a function of x, y, and z. I would have a component in the x direction, I have a component in the y direction, and I have a component in the z direction. This can be extended towards second derivatives, and the one that we'll see most often in chemical engineering is called the Laplacian. Here, it's represented as del squared. And what this is it's this second derivative, taking the gradient, dot producting it onto the other gradient. Okay, and so unlike before, right, with just the gradient, our Laplacian is a scalar, right? There's no x or y components in here. Okay, so that dot product, if you remember back, will give you a scalar. Okay, let's look and see what the Laplacian of this function is. And we've already calculated the second derivative, the second partial derivative of these functions with respect to x and y on previous slides. That's shown over here. All I need to do is take these sets, plug them in. So my second, my Laplacian of z is equal to this term, which is 2, plus this term, which is 0. So my Laplacian is 2. This gets a little bit more complicated in cylindrical coordinates. Remember that I can convert any of my functions between Cartesian and non-Cartesian coordinates through those functions that I showed on the first and second slides. Extra term which sort of feels a little bit odd, but this so when I take the gradient of f in cylindrical coordinates, I get my term my partial derivative with respect to r of my function in the r direction. But when I go to take my derivative, my partial derivative of the function in the theta direction, so how I'm moving around the circle, I have to have a 1 over r out front. So I take my derivative with respect to theta, and then I just multiply by 1 over r. Z is nice and friendly. Again, I just take the partial derivative with respect to z. Okay, I can go ahead and I can take the Laplacian of in cylindrical coordinates. You'll notice that this becomes a little bit more complex again. This has to do with, once again, these conversions between Cartesian and cylindrical coordinate systems. Okay, so looking at the contribution from the r dimension, I first take the derivative with respect to r of my function, and then I multiply it by r. After I've multiplied this whole thing by r, then I take my partial derivative with respect to r a second time. And after I get that, then I divide by r. In terms of theta, it's a little bit less complex. I take my second derivative with respect to theta of my function, and then I multiply by 1 over r squared. And z is the easiest of all, where I just have my partial derivative with respect to z. I can take these same concepts and apply them to spherical coordinates. Again, my r term for my gradient, my r contribution is simple. I just take my derivative with respect to r. When I take my derivative with respect to theta, I end up with that same 1 over r term. But now when I take my derivative and look at the contribution in the phi direction, I have this term that's a little bit more complicated that comes out front. It's 1 over r sine theta. Okay. And then I can, of course, take my Laplacian. You're going to see sort of similarities in here. I end up with a 1 over r squared partial with respect to r. So that has to happen after I've taken the first derivative of my function and multiplied by r squared. In terms of theta, I need to take my derivative with respect to theta, multiply that by sine theta, and then take the derivative again with respect to theta, then multiply all of that by 1 over r squared sine theta. And then finally, we have our contribution from the phi direction. I take my second derivative with respect to phi, and then I multiply it by 1 over r squared sine squared theta. Okay, let's move on and think about integrals. So remember, a definite integral of a function is the area under its curve, under that curve, right? So here's my function. I'm going to take the definite integral from some point A to some point B. What I'm really doing is saying how much area lies under this curve here. Okay. So I have A and B, which define this point and this point, and I'm looking to see how much area lies under that curve. An indefinite integral, which is shown down here, where I don't have A or B components, is the function that's the antiderivative of the given function. So in essence, how do I undo taking a derivative? So let's do a quick example in one-dimensional space. So I have f of x, say, is 3x squared. The derivative from 1 to 2 of that function, I can take that function, substitute it in there. I first take the antiderivative of this. I get 3x, of 3x squared is x cubed plus our constant c. Now I need to substitute now to do the that definite part to see what's the area under that curve from, say, 1 to 2. I use this convention, this line, which shows that I'm going to substitute 1 in and subtract that from when I substitute 2 in for x, right? So I get 2 cubed plus c minus 1 cubed plus c. the c's cancel out, and I end up with 7. I can do the same thing in a two-dimensional space where I take the area under the curve. So here's my curve here, well, the area under the plane, and I would look over some sort of x and y space and look and see what we have. So I can take, say, the derivative, the integral of f of x with respect to x from 1 to 3 and y from 2 to 4. And we can do this by taking these in chunks. Right, so first I substitute the equation in. I'm going to first look at this piece with respect to x. Okay, so what is the antiderivative of x squared? Well, it's 1/3 x cubed. What's the antiderivative of 4y with respect to x? Well, that's 4xy, right? I add in the x. And then, of course, plus c's, but those c's are going to cancel out like we saw. And I need to take that from 1 to 3. Okay, so what does that equal? I have 1/3 3 cubed plus 4 times 3 times y minus 1/3 1 cubed minus 4 times 1 times y. Right? So I can take all of these, and we'll notice that now x is integrated out. After I do these substitutions, x no longer appears. I'm left with 8 2/3 plus 8y. So now I'm just taking the integral. I'm left with taking this integral from 2 to 4 of 8 2/3 plus 8y with respect to y. What's the antiderivative of 8 2/3? Well, it's 8 2/3 y. What's the antiderivative of 8y? Well, it's 4y squared. And I'm going to go from 2 to 4. I can do out this math, and we'll end up with 65 1/3. Okay, so again, we can do this switching the x and the y components. So let's go through this relatively quickly. Here, you notice that dy is now the first set in this dx dy, and then the integrands over which I'm integrating have also switched, right? So 2 to 4 matches this y, 1 to 3 matches the x. Okay, so I've substituted in my equation, and now I'm going to take this integral with respect to y, because that's what's first. My the integral with respect to y, of course, is yx squared plus 2y squared. I'm going to go from 2 to 4. Okay, when I do this subtraction out, I get 4x squared plus 2 times 16 minus 2x squared plus 2 times 4 dx. Or I'm left with the integral from 1 to 3 of 2x squared plus 24 dx. All right, great. Now we're ready we've integrated out y. Now we're ready to integrate out x. So let's take the integral of 2x squared plus 24. Well, that gives us 2/3 x cubed plus 24x. I'm going to do this from 1 to 3. I do out the math, the arithmetic, and I'm left with, once again, 65 1/3. So what you'll notice, just like in taking our partial derivatives, the order of taking our definite integral doesn't matter. Whether I do y then x or x then y, I always end up with 65 1/3. Again, be careful, though, as you're switching these back and forth, that you keep the integrands associated with the appropriate dimension over which you're integrating. Okay, so not only can I do these integrals over space, I could consider them on functions, right? Because with respect to y, x is considered a constant, right? So I could integrate over y from y equals 2 minus x to 4x. So let's look at how we can do this equals x squared plus y, right? So I just substitute this into this equation. I'm now ready to take my integral with respect to y. The integral of x squared with respect to y is yx squared plus 4y. The integral is plus 2y squared. Now when I'm doing my what is y equal, I need to do it from y equals to minus x to 4x. I then substitute this in, right? So now instead of substituting in a number for y, I'm substituting in these functions of x. So we can see that we have x's all in here as I've substituted in. Now I'm not going to go through the arithmetic, but we would end up with an equation with respect to x, and then we can take that derivative and do the integral with respect to x. And this in the end would end up giving you 358.67. I recommend that you go through and you work out the math and you double check that you end up with this value. Okay, now that we've covered two-dimensional integration in Cartesian coordinates, it's time to move on to considering integration in polar coordinate systems. We're of course going to remember that r, the radial component, is the square root of x squared plus y squared, and theta is the inverse tangent of y over x. So therefore, we're going to convert our integral, our two-dimensional integral from x and y to r and theta. And so I can do that by substituting in these relationships into these integrands. When I do that and I do these substitutions and systems of variables, I end up getting this r out front. Okay, so everything else is going to stay the same, but anytime I'm doing an integral over a polar coordinate system, I have to include an extra r in here. So I take whatever function I have, I multiply it by r, and I have to do this before, I have to do that multiplication by r before I take the integral with respect to r. Same thing is going to happen in cylindrical coordinate systems. When I convert from x, y, and z to theta, r, and z, I end up having to have this extra r included from the change of variables. Okay, when I do this in a spherical system, I have a little bit more complex function that comes out front because I have a more complicated conversion into spherical coordinates. So instead of just taking my integral with respect to the underlying function of r, theta, and phi, I have to multiply by r squared times sine theta. All right, so when I'm taking the integral with respect to r, I have to make sure that I've taken this into account. And when I'm taking my integral with respect to theta, I have to take this into account. All right, so the last thing that I'm going to cover today are just the concepts of line and surface integrals. We're not going to go into detail in here because they're just not super common in chemical engineering. However, they do play a significant role in physics, electric, and magnetic systems. But I do want you to be familiar with the concept in case you run into it in any engineering conditions. So the concept of a line integral is the same as the concept of a regular integral in two-dimensional space, but instead of going over, say, a patch of x and y, I want to take my integral on a line. So in essence, what's the area under that curve, right? So here's this two-dimensional curve of z as a function of x and y. And I want to know what's the area along this curving path, right? So this is called a line integral. We can also do what's called a surface integral, where I have not just a line, but some sort of surface curve. And I'm going to take the area under that piece on that curve, right? And so these are represented with these sort of circular symbols to tell you that that's a surface integral. If you're interested in how to do these, there's lots of good videos both online and good textbooks on the different approaches to calculating line and surface integrals. Okay, so that's going to conclude our review of vector calculus. So you should now be familiar and capable of operating in three-dimensional coordinate systems. You should feel comfortable with the concept of vectors and vector fields. You should be able to take partial derivatives, gradients, and Laplacians of multi-dimensional space. You should be able to do multi-dimensional integrals in both Cartesian and three-dimensional polar coordinates. I'm remembering, of course, that if I'm doing integrals in three-dimensional, in multi-dimensional polar coordinates, I often have these sort of extra r factors, r's or sine thetas that have to be included. And then hopefully you have an idea of what line and surface integration are. As a reminder, please remember to take the reading quiz, and I will see you next time to talk about to talk about differential equations.